today we're going to look at section 6.2. Just a note before we start, we're going to assume all variables are positive, meaning you don't have to worry about the absolute value sign, and you also won't have to worry about dividing by 0 if you see a variable in the denominator of a fraction. So we're going to look at combining some ideas that we have studied before. If I see the fourth root of 80x to the 8th, I can break this into a product of the radicals. So certainly this is a legal step. And then from here, if 80 has any perfect fourth factors, such as 16, 2 to the fourth is 16, I want to factor it further. 16 times 5 is 80. And then if I look here, well, this is really, remember, x to the 8th to the 1/4 power. So in the end, fourth root of 16 is 2. Fourth root of 5, that just stays. That would be a decimal. And then the fourth root of x to the 8th power, or 8x to the 8th to the 1/4 power, that would be just x squared. X squared times itself 4 times x squared times x squared times x squared times x squared would give you x to the 8th. So your answer then should be 2x squared times the fourth root of 5. So today you might be presented with problems like this. If I can simplify the radical, let's just review. If the exponent on the variable is higher than the index, so for instance, if this is larger than the index, which is 5 in this problem, then I'm going to need to simplify this x term more. And if there is any perfect fifth factors of 64, I'm going to want to simplify that constant 64 more. So at this point, I'd be thinking of, for perfect fifth factors, 32 is a perfect fifth factor, and 32 times 2 is 64. You could also complete a factor tree. I'll show you that in a moment. And then I'm going to break down x to the 8th into perfect fifth factors too. So I'm going to say x to the 5th, and then I'll take the 5th root of, there'd be 3 x's left. The 5th root of 32 is just 2. 5th root of 2 would give me a decimal, so I'm going to just leave that. Now here, as long as the variable is positive, the 5th root and the 5th power, those will just cancel each other out, so that term would just be x. And on the last term, your exponent is smaller than your index, so we will just leave that. That's in simplified form as the 5th root of x cubed. And then if I combine these to get my answer, I have a 2 out in front of the radical, an x out in front, and then you have a 5th root of 2 and x cubed, putting these terms and just combining them under the radical. That's your most simplified answer. A couple of additional notes. This is how you could use the factor tree to get the same answer. You'd be looking for groups of 5. So there's a group of 5 that 2 would go out front, and then anything left over would stay under the radical sign. That's another way to get the 2 times the 5th root of 2. Another way to simplify the x term, if you look here, you'll start noticing a pattern. If you take 8 divided by 5, well, 5 goes into 8 once, and there's 3 left over. So that means there should be 1x out front, there it is, and 3 x's left over under the radical sign. So with the example that we just did, why don't you give this a try? Pause the video at this time. So if you started by factoring, here are a couple different looks. Let's look at the top. Maybe you factor the expression into something like this. The cubed root of 8 is 2. Cubed root of 9 would be a decimal, 2 point something. You just leave it. And now maybe you broke this down into groups of x cubed. So the cubed root of x cubed goes undo each other as long as, so those undo each other, excuse me, so you'd have x, and then I have the cubed root of x, that would stay. And the y, there's really no problem because the exponent is smaller than the index. So you can just leave that as the cubed root of y squared. And then your final answer should be 2 this would be x squared out front. And then under the radical, you have the 9, you have the x, and you have a y squared. Now, instead of breaking it down into these individual x cubed terms, maybe instead of this, you did something like this. You could break down that x term into the largest multiple of 3 for your exponent. So on the bottom, if you prefer this method, you should get the same answer. Give it 2, cube root of 9. Now the cube root of x to the 6th, that would be like x to the 6th to the 1/3. A third of 6, or 6 divided by 3, is just 2. So that would be an alternate route to getting the x squared term. And then we'd be to the same spot, same answer. You also could use a factor tree to get the 2 cube root of 9 if you prefer that method. So recall that, radicals, if I see the radical sign, that's like the 1/2 power, or the cube root sign is like the 1/3 power. So these properties that we studied for exponents hold for radicals. For instance, here this is like 4 squared times 3 squared. As long as I have a product, that exponent is attached to each term. Similarly, if I have the square root of 4 times the square root of 5, I can write that as the square root of 20. So on the previous problems, we've been kind of factoring radicals to get this, but certainly we can go the other way and multiply radicals as long as they have the same index, or as long as I'm taking the same root. I can combine them under one radical. So take a look at these, maybe pause, think, can you combine the terms? Which of these would work? First one, I can't combine these. These have different indices. I have a cube root and a square root, so I certainly can't combine those under one root. Second one, this is perfectly legal. I have the same index, so I could combine these and say the cube root of -8. Now, why is this helpful? Well, the cube root of 4 is a decimal, the cube root of -2 is a decimal, but if I multiply these together, the cube root of -8 actually gives me an integer. So that makes life a little bit easier by combining those radicals. On the bottom one, this does not equal the cube root of 5 plus 2. This is totally illegal to combine these if you're adding. We looked at this before, I think. You can't say the square root of 4 plus the square root of 9 equals the square root of 13. 2 plus 3 is not the square root of 13. Totally illegal. This is the same reason why you can't just say, I can't just distribute this in. You would instead have to FOIL this out. So as long as I'm multiplying, I have the same index, I can combine this product, those terms, under one radical. So this allows us to complete problems such as example 3. I don't really know what the square root of 6 is. I can approximate it. I don't know what the square root of 12 is off the top of my head. But if I combine these, I get the square root of 6 times 12 is 72. If I combine my x terms, I have x cubed times x gives you x to the 4th. And then I have a y squared times y cubed, which is y to the 5th. And then from here, we can simplify. If you want to try this on your own, pause the video. So 36 is the largest perfect square factor of 72. 36 times 2 is 72. And then I'm just going to leave this as a square root of x to the 4th. Since 4 is a multiple of 2, that'll clean up nicely. Now 5 isn't a multiple of 2, so for this y to the 5th term, I'm going to actually break this down into the square root of y to the 4th. So I'm going to leave 4 y's there, which would be 1 left over. That would be the square root of y to the 5th, broken into a product. And then next line, square root of 36 is 6. Square root of 2 stays. Square root of x to the 4th, this would just be x squared, or 4 divided by 2, 4 times a half. And think about it, x squared times x squared is x to the fourth. This would be y squared. Again, y to the fourth to the 1/2, 4 times a half gives you that 2. And then the last term is just going to stay as the square root of y. So now any terms not under the radical, just put all those out front, and then the terms left under the radical, 2 and y, multiply those together. That is your most simplified answer. Now recall from our study of exponents, if I have an exponent outside the parentheses, that exponent will go to every term inside the parentheses. So what I have on the right, this would actually be equivalent to what's on the left. And then if I look down at this example, if you're dividing radicals with the same indices, so same roots, this would be the square root, you can combine them under one radical, just like we looked at with multiplication. So up top, on the top of the page, this is really like the square root. That's saying the same thing as this. So, well, okay, so this is equivalent to what I have on the right side of the equal sign. Then I should be able to combine these under one radical and say, well, I'm taking the square root of 18x to the 7th over 2 times x to the 3rd. This is a perfectly legal step as long as your index is the same. Why is that helpful? Well, now 18 divided by 2 is 9. X to the 7th divided by x cubed would be x to the 4th. So 3x's in the denominator, cancel with 3 in the numerator. Then I could break this apart. The square root of 9 is just 3. And the square root of x to the 4th is x squared. Final answer. If you want to give this one a try on your own, that would be lovely. So pause the video at this time. So I combine these under one radical, and then let's clean it up the inside up and we can worry about the fourth root. This isn't the only way to approach this problem, but it's one method. So 96 divided by 2, 96 over 2 would give you 48. If I look at my y's, I have 26 y's in the numerator, 3 in the denominator, so 3 in the denominator would cancel with 3 in the numerator. You have 23 y's left. And then that x squared term, or x to the negative 2 power, if I cross the line, change the sign, bring that to the other side, the numerator is a fraction. Now I can worry about cleaning up this single radical. So fourth root of 48. Well, if I think of my perfect fourth factors, 16 is a perfect fourth. 2 to the 4th power is 16. So I can say, well, square root of 48 is the same as the square, or the fourth root of 48 is the same as the fourth root of 16 times the fourth root of 3. For this y to the 23rd, I could break this down into y to the 4th term, but instead, I'm just going to write this with the exponent as the largest multiple of 4, that's less than 23, so we'll go y to the 20th. And then I'd have 3 y's left over. So that gives me y to the 23rd. And then also I have the fourth root of x squared. Now if I keep simplifying, the fourth root of 16 is 2. Fourth root of 3 is not an integer. Why did I break this into y to the 20th? Well, this is like y to the 20th to the 1/4 power. So 20 times a fourth, or 20 divided by 4, is just 5. So this term right here is actually just y to the 5th. Then I also have the fourth root of y cubed, which I'll just leave because the 3 is smaller than 4. And the fourth root of x cubed will stay because the exponent, again, is smaller than the index. So your final answer should be 2, y to the 5th,
And under the fourth root, you have a 3, an x squared, and a y cubed.